Okay. All right, guys, just give me a sec. Okay. All right, guys. If you can hear me, let me know. I'm just setting everything up. Sorry for the delay. I apparently can't work technology that well. Can you guys see that whiteboard okay? Cool. Okay, you guys can hear me. I'll take it. All right, let me just finish this up and then we'll get started. Okay, guys, can you see that whiteboard okay? It's a little low. I tried to get it higher, so I don't know what's going to happen. Okay, I'm getting yeses. Cool. Yeah, I'm going to save this afterwards. It should save automatically. I was playing around with it earlier. Okay, guys. Let me see if I can position this a little higher. Please ignore my face. Yeah, okay. It's a little tilted. I think that's going to be a problem. That should work. I have it on like a tower of pillows. Yeah, okay. All right. I just need my phone and then we can start, guys. Okay, guys, once I find my phone, we're going to get started. It just has all the questions I want to do. Okay, got it. Where'd you guys go? All right, guys. Sorry for all the delay. Sorry for my face in your face. Okay, here we go. Dave, I got it. Thank you. Okay, guys, let's do this. So, it's gonna be weird because obviously I can't interact with you guys like I normally like to, but we'll do it anyways, and we'll get through as much as we can. Okay. Blah blah blah. Okay, you guys don't have any questions, so we're good. So let's just get started. I posted the handout already for you guys. You guys should have this. Right, it has all the info. I think that's pretty useful. Let's just run through it real quick together. Like, I'm gonna try to orchestrate this like it were in person, right? So if this were in person right now, you'd be paying attention, not texting, whatever. I don't care. You're home. Just make sure you guys pay attention to get as much use out of this as you normally would, okay? So the first slide, it just says exam 3 review info. Then I have some info on E2, SN1, SN2, leaving groups, E1. And then if you guys look on the E1 slide, it says Williamson ether synthesis and the protecting group. Okay. Then if you guys look, I have converting OH into a good leaving group on there. The oxidation reduction reactions, those are these guys. Right? In lecture, it looked like that. Uh-oh. I think we have one issue I didn't anticipate for, guys. The wording comes up backwards. This is my life. Okay. Great. I'm not going to write backwards for the next 3 hours. Hold on. Oh, it's good for you guys? Okay, just as long as you guys say it's good. On my screen, it shows it backwards. That's mad funny. Okay. I've never done YouTube Live, so like this is some funny shit. Okay, so apparently you guys can see it just fine, which is good with me because then I don't have to fix anything. Oh yeah, okay, sorry. That was my voice. I was just testing it out. Okay, cool. All right. That would have sucked. Okay, so you guys learned it NaBH4 over ETOH. Right? Now, if you look at the slides I posted, I gave you guys numbers. Just ignore those numbers. Okay? Just ignore the numbers I gave you guys and go with this. And I think I wrote that on the slide anyways. Everything else on that slide is good, though. Okay. The next set of slides are all HNMR, CNMR, and that stuff. You guys are going to learn CNMR tomorrow, from what I understand. I'm still going to help you guys out with the workshop right now, just to give you a good gist of what's going on. But with HNMR and CNMR, you want to use IHD, which we did on the first exam. I'll run through that. This is all essentially just info for you guys, okay? For those of you guys who just like the information in front of you, that's what this is going to be used for, okay? All right, and that's literally what the rest of this is. It's just all HNMR and CNMR, and I'm just going to walk you guys through it instead of talking about it for 3 million years, okay? So let's just get started with a problem, and then we'll go from there. Let me see if I can get the laptop closer, just to give you guys a better view of the whiteboard. Oh, yeah. Okay. There's like a blind spot, but that's fine. Okay, much better. Now you guys can see it better. You're closer and you're eye level. So just ignore me. You're going to see like half my body in the video, which is fine. We'll just go with it. Okay, so here we go, guys. You guys sent in your questions. I already have them. Let me pull them up. I want to start this by giving you guys just a super, super brief intro to HNMR, CNMR, stuff like that, because I think that's most important. I guess my face is going to be cut off. That's fine. As long as you guys get the gist of this stuff, we're good to go. So HNMR and CNMR. Let's start with CNMR because it's more basic. So when we're thinking about CNMR, right, that's carbon NMR. The only thing you're looking for in CNMR is unique carbons. What's a unique carbon? It's a carbon that doesn't look like another carbon. Are you guys able to read that? Are you guys able to read that, or should I write bigger? Let me know. Yeah, you can read it. Okay, cool. So you're looking for unique carbons. So let's take, for instance, something like this, okay? So here's your structure, and let's say I number this. Not that you have to, but I'll just number it. Right, 1 through 4, just so it's easier for me to reference. And I'm gonna write out all my CH3 groups when I do CNMR because it makes my life simpler. So usually they'll say in a question, like how many resonance peaks are there, how many signals, stuff like that. All that means is that it's just asking how many unique carbons do you have. So when you're looking at this compound, you have the CH3 group here, right? And then you have 2 CH3 groups here. Now, what you want to ask yourself is, are all 3 of these CH3 groups the same? And the answer is no, they're not all the same, right? Because this CH3 group is connected to a carbon containing 2 hydrogens, whereas this CH3 group is connected to a carbon containing 1 hydrogen, right? So these are not the same CH3 groups. What about these CH3 groups? Are these the same CH3 groups? And the answer is yes, they are, because they're both connected to the same exact thing, right? They're both connected to carbon 3, and they're both connected to 3 hydrogens. So these 2 would result in only 1 signal, okay? So those 2 together would be the same signal. This guy would produce his own signal, right? Carbon 2 doesn't look like anything, and carbon 3 doesn't look like anything, so they would also produce their own signals. Is this making sense to you guys? This is weird. Usually I like to gauge your reactions. So how many signals total would this structure show? What do you guys think? This is like a bad episode of Dora the Explorer. Hopefully you're laughing at me right now because I can't tell. 4. Yeah, there's going to be 4 peaks, right? So we're going to have 4 unique carbons on this structure, right? That's not so bad. Hopefully you guys agree. So this guy's going to show 4 unique carbons, okay? That's essentially CNMR. When you look at CNMR on a graph or a plot or whatever these things are called, right? Usually it's going to go from 0 to 200 ppm. Okay, ppm is parts per million. So usually it goes from 0 to 200, and they'll just show you peaks and shit like that, whatever. If you have 4 peaks, you have 4 unique carbons, right? So because this guy has 1, 2, 3, 4 peaks, it's telling us that it has 4 unique carbons. So it's a contender for this one. This one's not going to look like this. I just made this crap up. But just to give you guys an idea of what to expect. Okay? So now, when you're looking at this guy, right, this is CNMR. HNMR is super complex and fucking annoying. Okay? With HNMR, you're still going to have a ppm scale, but the values only go from about 0 to 12 at most, right, for HNMR. So if you're confused on how to identify each, just keep in mind that CNMR goes from 0 to 200, and HNMR goes from 0 to 12-ish, sometimes 10, sometimes 8. Okay? So let me throw up a question for you guys to do, and then we'll run through it together, and we'll have some fun. If I can find it. I have a whole document, and then my printer also decided not to work today, and I'm carless. So it's been a week, guys. It's been a week. But I'll be in workshop tomorrow, and we'll have fun and everything. All right. So on your workshop quiz, I think it was the first question. Let me pull it up. Yeah, how many peaks would you expect to see in this spectrum? Right now, I'm going to start with the newer stuff, obviously, because you guys really know the older stuff by now. Can you guys see that okay? It's a little glary. This is just an NCH3. That's an NCH3. Okay. So now when you're looking at this, you want to ask yourself how many unique carbons. Before you even get there, ask yourself, is there symmetry? And this is workshop question 1. Right? Is there a plane of symmetry here? And the answer is yeah, there is. We have symmetry right down the middle. That means everything on this side is the same as everything on that side, right? So now you want to ask yourself, how many unique carbons do you have? And what do you guys think you're going to have here? Take a minute to try to do it. Don't use the answer that you got off of a friend. Someone said 4. What else do you guys think? 4, 3. Okay, so we're getting some mixed signals between 4 and 3. The answer here is going to be 3. Let's talk about why. So the first thing you want to ask yourself is, are these carbons the same? Right? And the answer is yeah, they're the same carbon. They're both connected to 3 hydrogens, and they're both connected to a nitrogen atom. So these count as one signal. Okay? Then this carbon is a CH2. This is also a CH2, but they're different CH2s. How do we know that? This carbon is connected to nitrogen. This carbon is connected to another carbon. So because of that, that's its own resonance. We'll call that 3. And this is its own resonance. We'll call that, we'll call that 2, and we'll call that 3. Right? And then hopefully what you guys realize is this carbon is the same as that carbon. And then these carbons are both 1. So you only get 3 signals. Okay. Sorry if I get close to the screen. It's just so I can read the comments, make sure no one's confused. Everybody good on this? Not bad, right? It's like when you take 5 seconds to just look at it, it actually makes it a lot simpler. Okay. So that was an HNMR question from your work, CNMR question. Don't believe you guys really had any other CNMR. A lot of them were just HNMR. Yeah, okay. And remember, I'm not going to do the whole workshop. I'm just going to go through a few of the questions with you guys. So that's essentially CNMR in a nutshell. Let me do HNMR. And I want to get rid of that light bulb because it's annoying the crap out of me. I don't like when things glare. I have a light bulb in my room that glares. This isn't my room, it's a spare room. But like funny shit. Okay, I've done enough talking today. Let's talk about HNMR. HNMR is complex, okay? It's got a ton of crap going on. If you're in Orgo Lab, you probably just half-assed it to get through on the theory quiz that we just had. But HNMR is showing the amount of unique hydrogens, right? And all this info that I'm giving you is in the handout, okay? And remember that handout doesn't include everything, but it'll give you the vast majority. So we're talking about unique hydrogens. If you can identify a unique carbon, you can identify a unique hydrogen, right? It's the same crap, except it's an H instead of a C. So we have unique hydrogens. Okay. What did I do? Yeah. All right. So each signal that you see on an HNMR plot will be a different hydrogen. Now, like we said, it goes from about 0 to 12-ish ppm. Okay. There are 3 words I want you to know. The first word is chemical shift. The next word is integration. And the last word is coupling or splitting. Right? So we have unique hydrogens, chemical shift, integration, and coupling or splitting. Those are 3 key words for HNMR that you guys are going to see over and over again. So what is a chemical shift? A chemical shift is just where your signal is on the x-axis. right? That's all the chemical shift is. We're saying it's either shifting to the left or to the right, okay? Now, if we say something is shifting, I don't want to mess this up. If we say something is shifted to the left, we call that downfield. That's a shift to the left. If something is downfield, we're saying it's shifting to the left, okay? Upfield would be a shift to the right. Like I said, it's all in the handout, so I don't want to spend too much time writing, okay? All right, so that's that for chemical shift. It's just where it's located, right? Now, the integration number will tell you how many H's you have, right? So if you have a singlet, which is just one peak, and it says 3H, your integration number is 3. So it's telling you at that carbon you have 3 hydrogens, okay? That's all your integration number is telling you. So it's just telling you how many hydrogens are giving rise to this signal, okay? Just an aside, another name for HNMR is proton NMR. You might have said that. That just means HNMR as well, okay? So integration tells you how many H's. That's pretty straightforward. And then coupling or splitting, that is, okay. Coupling and splitting is where you get your different, like, phrases, I guess you can call them, or different names, what we've been using. A singlet, a doublet, a triplet, a quartet, a pentet, a multiplet. After triplet and quartet, I just ignore everything else and I call it a multiplet. Multiplet. Good thing I'm not an English major. And a multiplet, right? So these are the amount of unique hydrogens that you have, right? So you can have a singlet, a doublet, a triplet, a quartet, or a multiplet. And these things will tell you different pieces of information. A singlet is 1 peak, right? Doublet, 2, triplet, tri, 3, quartet, core, 4, multiplet, more than 4. Okay. Yeah. Okay, cool. So that's it for coupling, right? It's just the different signals that an HNMR spectrum can give off. Okay, and all this stuff makes more sense in real practice. I hate lecturing. So let's just get on with it, shall we? Let's do a workshop question, which is what anybody cares about. So unique hydrogens. So when you're doing splitting or coupling or whatever you want to call it, we have a rule. It's N+1, right? That will tell you how you're splitting. So that will tell you whether you're a singlet, a doublet, a triplet, a quartet, or a multiplet. Now, N refers to the adjacent or the neighboring hydrogens. Right? And these neighboring hydrogens are hydrogens that don't look like the one you're currently looking at. And I'll say that again, and it'll make more sense in a second when we do a question from your workshop. But so N+1 is your neighboring hydrogens, okay? So let's do this workshop question that you guys had. That's ugly. I think this was like 2 or 3 or something. I don't know. I have it somewhere. And they want to know how many signals, right? Yeah, number 3. So they want to know what would be the expected splitting pattern of the signal associated with the indicated hydrogen atom. Okay, now remember, when you're doing HNMR, you're just looking at the neighbors of this guy to see what he's going to see. Okay, so anytime I'm approaching HNMR, all I like to do is draw out all my hydrogens to start, right? I want to make sure I have everything correctly laid out. So we have 2 hydrogens there, 2 hydrogens here, and 2 H's here, and 2 there, right? Now you want to ask yourself, is this molecule symmetrical, right? And what would the answer to that be? Yeah, right? It's symmetrical. It has symmetry down the center. So would you guys agree then that this hydrogen with a circle is the same as this hydrogen with a circle, right? And then this hydrogen, this carbon with a star is the same as this carbon with a star, right? So these aren't oxygens, these are just circles. So these two carbons are the same, these two carbons are the same, which means that these H's are the same, right? And these H's here, these H's are the same, okay? Is everybody good with that so far? Just let me know. Because once again, I wish I could see your guys' faces so that way I'd know how to appropriately respond. Yeah, okay, good. Like 2 of you guys are still listening. We're good. So these are the same carbons. These are the same carbons. Now we want to look at this. So how many neighboring hydrogens does this carbon have? How many neighbors? What do you guys think? How many neighboring hydrogens does this carbon have? Does it have 2 or does it have 4? Two, 2, 2, 4, 2. Yeah, okay. So this guy, he appears to have 4 neighboring hydrogens, right? So what most of you guys did for your workshop quiz is you did n plus 1. You did 4 plus 1 is 5. Wow, 4 plus 5. Okay. 4 plus 1 is 5. And you got your pentet, or whatever the hell that is, right? But that wasn't the correct answer. The correct answer for this question is a triplet. And the reason being is because this carbon and this carbon are the same, and these hydrogens are the same, these hydrogens over here cannot be the neighbor of this hydrogen because it's the same hydrogen. And that's probably one of the more difficult things you guys are going to have to understand on this topic, is that because these are the same hydrogens, right, it can't be its neighbor. So these don't count as neighboring hydrogens. These count as your only neighboring hydrogens. So this carbon would see a triplet. Yeah, there we go. Okay, yeah, I'll do a different example with that's not symmetrical. But yeah, so this is a piece of crap question in my opinion. Hopefully you guys are laughing at this crap. I don't know. We'll see. Just trying to Dora the Explorer this whole thing. Bum, bum, bum. So that we would see a triplet. Okay, let's do another example. Let's do something you guys will probably see more often. You guys love these. Okay. This is a shitty question. Hold on, guys. Let's just do this. Okay. Something like this, because this is something common you guys will see. This is a CH3 group here. I don't know if that glare is bothering you guys, but on my end, it's pretty freaking annoying. All right. This is from the light bulb. So in this question, remember what I said. Always draw out your hydrogens. Okay, so you always want to draw out those hydrogens. Maybe I can move this over in a second. All right, so we draw these hydrogens, and this one does have symmetry, but that's okay, right? So in this case, because they're not right next door to each other, I can draw a line straight down the middle of this. And what we'll notice is that this H and this H are the same hydrogen. This hydrogen and this hydrogen are the same hydrogen. And then this one is different. than this one. We'll give it a smiley face. Right? So here on this spectrum, we would expect to see 1, 2, 3, 4 signals. 4 signals. Now you want to ask yourself, how are they going to appear? Right? Well, this carbon has how many neighbors? It has 2. So you would do 2 plus 1 to get a triplet for this guy. Same thing here, right? It has 2 neighbors, triplet. This guy is the same hydrogen, right? 2 neighbors, triplet. This guy here has only 1 neighbor, so you do n plus 1, and you get a doublet. Okay? This guy over here has no neighbors, so you do 0 plus 1, and you'll get a singlet. Yeah, I'll explain it all again. Give me 1 second, guys. Let me see if I can shift this over without injuring myself. I have like a mini fridge in the spare room that I'm using as a stand because my stand decided to not work today. Okay. Well, that's awkward. Okay, better. I like it better. Okay. Let's run through this again, okay, guys? So with this, right, let's take it from the top. Okay, so the first thing I did was I drew out all my H's, right? Then I said I had symmetry. And then we identified that these 2 H's were the same. These are the same. This was different. And this was different, okay? Now remember that when we're assigning signals, you are always looking at your neighboring hydrogen, right? So we're looking at neighboring hydrogens. So let's look at the CH3 group to start, okay? How many neighboring hydrogens does your CH3 group have? It has 0 neighbors. So in order to determine its splitting, we plug it into n plus 1. So you do 0 plus 1 is equal to 1. That gives us a singlet. Okay? Then you look at this carbon here, and you notice that it has 1 neighboring hydrogen. Then you add 1, you get 2, that gives you a doublet. Okay? Then this hydrogen has how many neighboring hydrogens? You guys tell me. This carbon, how many neighboring hydrogens here? Yeah, it has 2, right? This carbon has 1, 2 neighboring hydrogens. You add 1, you get a triplet. Okay? And then here, this carbon, or this hydrogen, has 2 neighboring hydrogens. So you add 1, and that also gets you your triplet. Okay, does that make more sense the second time around? What I would suggest you guys do, because your exam is on Monday, if you finish workshop early tomorrow or Thursday, don't leave. Some of you guys make like a mad dash out the door, and I get it if you have other things to do. But if you finish early and you know you have to be there for an hour and 20 minutes anyways, just stay and ask TAs questions, okay? Ask them what's going on. Ask them if they can explain it to you a little more. You know, anything you have questions on, just wait until you finish the workshop. And then once it's finished, ask TAs any questions you have. And just use that time almost as like an extra office hour session, okay? And someone wants to know how come the CH3 has no neighbors. So the CH3 is connected to this carbon. This carbon already has 4 bonds, right? 1, 2, 3, and then the double bond. So that's why there's no hydrogens there. So it has no neighbors. Okay? Hope you guys are finding this useful. I know it's a weird environment. Okay, let's do... Yeah, let's do this. How many HNMR signals, or how many signals would you expect from this HNMR? I want you guys to take a minute and tell me how many signals you would get from this compound. Okay, so take a minute to try it on your own. After this question, we're going to move on to a workshop question. And then I'll do 2 workshop questions, and then we'll move on to the review stuff. Now, 5, 5, I'm getting 5 as an answer. If you didn't finish yet, don't worry. Take your time. I'll give you guys another few seconds. For your guys' final exam, keep in mind that it is, we have Thanksgiving, right? And then we have a week back from school. During that week of school where we come back, that's the last week of TA office hours. So just make sure you guys use them. Once finals start, we don't have to hold office hours. So make sure you use them while you can. Okay, I'm not going to be able to do another review for the final, unfortunately, just because all of my finals this year are cumulative, which is real sweet of my professors. They're really God's gift to earth. But yeah, but definitely I'll still have office hours on Fridays and stuff like that. So definitely abuse those. So let's take a look at this, okay? First, you draw out all your H's. It's a CH3, CH3. This is 2. That's 1. That's 2. Be careful with this H. I almost forgot, which I'm sure you guys did too then. So now, when we're looking at this compound, let me draw it up a little bigger. Somebody said 5. Let's check to see if that's true. Okay? Let me draw it down here a bit. Okay, so let's ignore all the CH3s because those just get annoying. Let's start here. That's the only carbon with 1 hydrogen, right? So we know that that for sure is going to count, right? So this guy is a definite signal, so I'll give that a smiley face. That's 1 signal. Now I have 2 CH2s, right? However, the hydrogen on each of these CH2s is different, okay? And the reason they're different is because this CH2 is connected to 1 H here and 2 H's there, right? But this CH2 is connected to 1 CH3 here and 2 hydrogens there. Because of that, that makes these different. So they each count as their own. So this is 1. I'll give that a star, right? This is another 1. Give that like an asterisk. So these are 2 different CH2s because they're connected to different things. Okay? Then, when we look at this carbon, this CH3 is connected to 2 hydrogens, right? Now, this CH3 is only connected to 1 H. So these are different CH3 groups because they see different things in their neighbors. Okay, so this is a different group. So I'll circle that. So we're at 1, 2, 3, 4 so far. Then you look at your 2 CH3s and you notice that these hydrogens are the same because they're connected to the same thing. So these guys would count as their own. So they count as 1 because they're the same. So altogether, we do get 5 HNMR signals. Okay? And that's how that would work. Let me drop one of your workshop questions. It's just going to take a minute because it's a long graph chart thing. Someone asked how the finals impacted into your grade. For your final, it's out of 180 points. I'm going to do workshop quiz question 4. Your final exam is out of 180 points, so it's worth double of a regular lecture exam. It's also cumulative. Whatever you do on the final, it'll definitely significantly boost your grade up. Oh, wait. I'm sorry, guys. That's not what I wanted to do. No, wait. Sorry. What am I doing? Shit. Eraser down. Okay. So I wanted to do, not this question. I'm sorry, guys. We're going to come back to this. I'm going to move on from HNMR real quick, just because I want to get some other stuff in, and then we'll come back to it. Yeah. Okay. We're going to come back to this HNMR stuff, okay? You guys haven't learned it yet. You're going to learn it tomorrow. So definitely get the help from the CLC. If you do bad, will it ruin your grade? No, the final will not entirely kill you if you do poorly. However, if you guys do really well on the final exam, it will significantly increase your grade. So definitely try to put some work into it. I do have like a final study plan that I recommend for the final. If you guys just send me a message and remind me if I forget, I'll send you guys out what I think the best course of action is to study for the final to do the best on it. But let's just focus on this exam for right now. So let's do a question that I have. That looks like this. And then so in this question, they want you to draw the reactant X for the following reaction, okay? And this is a dashed N3. So I want you guys to take a minute, try to come up with X, okay? The best way to approach these problems is to first identify which reaction you are dealing with, okay? So first I want you guys to figure out what reaction is happening here, okay? You guys take a minute to do that, and then we'll do it. Okay, so you guys try to take a minute to figure out which reaction this is. I'm going to refill my water really quick, but let me know what reaction this is. Okay, guys, what did we get? Katie Lee, to answer your question, HNMR signals equaling CNMR signals. I don't want to say that's a thing all the time. For the last one, yeah, the HNMR signals would have equaled the CNMR signals, yeah. Yes, SN2, but not because it's aprotic, right? They could have easily gave you this without the solvent. The key thing to recognize here is that it's N3 minus. Remember, sodium spectator, so we cross it out. N3 minus is a weak base and a good nucleophile, right? And this guy's on a secondary carbon. So because it's on a secondary carbon, it could be SN1 or SN2. But because, oh, that's nice. But because this guy is a weak base, good nucleophile, it's going to end up going, like we said, SN2, right? And I'm just going to talk to you guys as if you were in front of me just to make this go a lot smoother. So if this were SN2, what do you know about stereochem in SN2? Does stereochem stay the same or does it change, right? And we know that stereochem is going to change. So that means X must have had a wedge and not a dash where the N3 is, right? You guys following me? SN2 changes stereochem. So if I were to draw this reactant, the methyl group here is entirely uninvolved in my reaction. Because it has nothing to do with it, it just stays the same. We don't touch it. Then you have to decide what kind of leaving group you're going to use. Here they don't give us a molecular formula and they don't tell us which one to use, so you can pick your favorite. I'm going to pick bromine because I like bromine as a leaving group. You could have also picked iodine or Cl, right? All of these would have worked as good leaving groups. Okay, so all three of these answers would have been acceptable. Yeah? Okay. This isn't too bad of a question, right? This is pretty straightforward. I just wanted to know what X is. Let's talk about the difference between these reactions because I think you guys are having the hardest time with that in terms of just figuring out when to do what for each reaction. Okay, so let's say we had a reaction that looks like this. I don't know where I'm going with this. Let's be real. Like this, okay? And they gave you water. Now, the chart that I gave you guys on that handout, it comes with like a small disclaimer. Just be careful. The chart works. I love it. I'm talking about this guy here. Let me bring it up to you guys. Yeah, this chart here, right? This was given to me by one of my TAs when I took the course. And I found it super useful. It's worked for me on just about every exam question except for like one or two. So I find it pretty reliable. But if you guys go down to where it says key, just so you guys have an idea of how to use it. If you come down here where it says key, primary, secondary, tertiary, those are referring to leaving groups, okay? So if you say that you have a tertiary leaving group, we know that this reaction for sure is not going to be SN2 because SN2 can't do tertiary, right? So if it's tertiary, it has to be SN1, E1, or E2. Normally, E1 will have heat present, so we'll ignore that for now. In terms of E2, we don't have a strong base present. This is actually a pretty weak base, and it's a pretty terrible nucleophile. And like I said, that's on your chart there. The charts are useful for a list of nucleophiles and bases and stuff like that. So then we know it's going to go SN1. Now, the first step in your SN1 reaction should be that your leaving group leaves, right? Leaving group leaves. So it just pieces out. You get a positive charge. Then water has to come in and attack. Now remember, these electrons are going to that carbon. I just drew it pretty shitty. I'll draw it nicer. So it's going to that carbon. From there, you get this intermediate. Yeah? Right? And then from here, all you're doing is you're deprotonating that H. And you get OH. Okay? On an exam, you would have to show all of these steps to get a 10 out of 10 mechanism. What the TAs understood from your last exam is that you guys don't really like drawing out intermediates. You guys aren't sure of yourselves when it comes to mechanism questions. Make sure you're drawing out intermediates, okay? Think of it like a math class, right? In a math class, you have to show your work to get the answer correct. If you just give them an answer, they're not giving you any points. Same thing with mechanisms, okay? You want to show all these intermediates out. Now, if you want to show something grabbing this H, you can. I could have showed another water coming in and grabbing it. That's fine, okay? But you don't have to show that. Now I want to ask you guys a question, right? So we say that SN1 results in a racemic mixture. Right? SN1 results in a racemic mixture. That means we get a mix of wedge and dash. Let's talk about why that happens. So when you're looking at this carbon, right, what you're hopefully noticing is that this carbocation, this carbon here, does not have stereochem because that carbon only has 3 things attached. Carbocations have a trigonal planar geometry, so they're almost incapable of having stereochem, okay? So if this has no stereochem, when the water adds itself, right, we don't know if it's going to add from the front or if it's going to add from the back. And because of that, that's why we say we get a mix of wedge and dash, right? We get that racemic mixture. Now, this compound doesn't have chiral centers, so I don't know if this would really apply, but for our purposes here, it's going to work, where you get these 2 products, right, in your racemic mixture. It's just a mix of wedge and dash. The methyl group here is wedge, and then the OH here is wedge, right? It's just that mixture of wedge and dash. That's all we're saying is happening for SN1, okay? Okay, I think you guys have a couple questions. Let me check it out. Okay, so the first question, can you explain what a good nucleophile likes to do versus a good base? Good bases will go and attack things and deprotonate them and steal hydrogens, right? So if you have a good base, it usually wants to grab a hydrogen. If you have a good nucleophile, it's usually going to want to attack, okay? I'm going to explain when the chart doesn't work. I got you on that one. I have a few examples lined up for you. So let's run through another type of example, okay? And I want to spend about an hour doing SN1 and SN2 with you guys just because I think it's really important to get all this stuff down. Let's do, I don't know. Let's do rates. Let's compare 2 things. I'll add some solvent in here. Not that it's necessary. Okay, so both of these reactions are going to be SN2. The reason I know that is if you get rid of sodium, I have Cn minus. In both cases, Cn minus is a weak base and a good nucleophile. Okay, I'll give you guys a minute to copy these down if you're copying down, and then I'll explain it. Just a reminder, I have office hours on Fridays at 11. This week, I'm going to have office hours on Friday at 11. I'm also holding extra office hours on Thursday at 1 p.m. I'll probably be there until like, let's go with like 2:30-ish. But if I'm there longer, I'm there longer. So Thursday, I'll hold extra office hours, okay? So if you guys need help, come through on Thursday. All right. Okay, so these reactions are SN2. And we know that because we have a weak base, good nucleophile, so we know it's going to attack. Right? And then this guy's going to kick out. And by doing so, it inverts the stereochem. Now, a question like this would want to know, which reaction here, let me see if I can move this up. Which reaction here is going to occur faster? Well, the only difference is the leaving group, right? CN is the nucleophile for both reactions, and DMF is the solvent for both reactions. So the only comparison here is Br versus Cl as a leaving group, right? So how do we determine what's a good leaving group and what's not, right? That's ultimately the ultimate question is that. How do you know if something's a better leaving group than something else without a trend to tell you? So the definition of a good leaving group is the stability once it has left. Okay, and I'll say that again. The definition of a good leaving group is the stability of that leaving group once it has left. Okay, so if these guys leave, you have Br minus and you have Cl minus. Who's better at holding that minus charge, Br or Cl? What do you guys think? Who can stabilize that minus charge better, Br or Cl? Okay, a lot of you guys are saying Br, some of you guys are saying Cl. Who has a bigger atomic radius, Br or Cl? Br, right? Br has the larger atomic radius. Because bromine has a larger atomic radius, there's more room for these electrons to move around, which makes that minus charge overall more stable. That's why Br is a better leaving group than Cl. Okay, so that's for leaving groups. Now, you guys might be getting confused between leaving groups and nucleophiles. In nucleophiles, that's when they're interchangeable depending on the solvent. Okay, but for leaving groups, you go based on the stability once it's left. Okay, so in this case, who's going to be the faster reaction? Reaction 1 or reaction 2? Reaction 1, right? Reaction 1 is going to be faster because it has the better leaving group. Okay? Yeah, you guys rock. Okay, cool. So that's for leaving groups. Okay? Another term for leaving group that he uses in lecture is electrophile. A leaving group is an electrophile, in case that word's been confusing you guys at all. Okay, so let's do another one now, where we vary stuff just a little bit. Let's do, I have one actually, a good one. Oops. You guys like my whiteboard? I'm a nerd. I have a whiteboard at my house. It's pretty sad, but also awesome at the same time. Whiteboards are fun. Cool people have whiteboards, just saying. Okay, for this, I want you to arrange these in order of increasing rate in an SN2 reaction. So for these guys, you're going to order them in terms of increasing rate in an SN2 reaction. Okay, that's what the question says. So are we looking at nucleophiles here, or are we looking at leaving groups? We're looking at leaving groups, right? We don't have any nucleophiles, so we're just looking at leaving groups. And what do you guys know about SN2? Who's the better leaving group? Primary, secondary, or tertiary? And you guys know it's primary, right? For SN2, you want a primary leaving group. Well, here, every leaving group is primary, right? This carbon is connected to one other carbon. This carbon is connected to one other carbon, and same for the guy down there. So then how do you differentiate if everything is primary? Well, there's a few ways to do it, right? The first thing we just established was that bromine is a better leaving group. Because bromine's a better leaving group, it's going to go the fastest. Yeah, someone said it in the chat. Nice job. Number 1 and 3 both have CLs, right? The difference between them is that number 1 has this branching going on that 3 does not. Because of that, that makes 1 slower and 3 a bit faster. Okay? Good work, guys. Very nice. Wouldn't it be a blessing to get some shit like this on your test? That'd be nice. Okay. So that's for that. Now I'm going to give you a set of reactions, and I want you to tell me which ones are going to lead to the same product. Okay, so take a minute, start to copy this down while I finish writing up the question. Okay. So take a minute to copy these down. The question here is which will lead to the same products out of all 4 of these reactions, right? Out of all 4 of these reactions, which reactions are going to lead to the same products, okay? So this is CO, NaCN, DMF. This is PBr3, NaCN, DMF. This is HBr, NaCN, DMF. And this is TFCl, NaCN, DMF. Okay, just in case if you guys can't read it. It's a bit glary, and I don't know how the view is from your end. But take a minute, copy these down, do all 4 reactions, and then tell me which ones lead to the same products. If any of you guys who are listening are in the 2:30 workshop tomorrow, I have a 10-minute gap before the workshop starts from 2:20 to 2:30. So like if you guys have pertinent questions that need to be answered right away, or you may very well die, just come see me in front, right before the 2:30 workshop. If you get there a little early, feel free to approach me and just ask me any questions you have, okay? That's an OH. But yeah, tomorrow before that workshop, or if you're in the 4 o'clock workshop, I'll also be there around 3:50. So I have a 10-minute gap between them too if you have questions. So just come find me with any questions you guys have tomorrow, okay? I'll be happy to answer anything. Yeah, TFCL. What's before it? Before TFCL, this is just a dashed OH. So this is a dashed OH. Sorry. This marker is not as good as I was hoping it to be. Move this a little closer. Oh, below TFCl. Yeah, that's pyridine. Good catch. Thanks, guys. Anytime. I wish this was in person, guys. It'd be so much better. But my car started fuming on the way to school yesterday. Good times. Last year I hit a deer. Fun fact. I just suck with car troubles. It's wonderful. Okay, copy these guys down, perform these reactions. Don't worry for anybody who's concerned about animals. The deer lived. My car didn't make it. Someone just asked, I'm dead. Yeah, the deer was fine. It ran off with no issue. It just banged up the whole front of my car. That was last year, though. Yesterday, I had like different car problems, but last year I hit the deer. Yeah, last year I was fine. Nothing happened. It was just the car that got fucked up. It's all good. But like I said, that was last year. This year, it's just the engine didn't want to work, so it's getting fixed. You guys are so nice. Okay. Let's draw in some products. First thing you want to do is figure out the reactions. Okay? So for number 1, this is going to be SN2. So all we're doing is inverting the stereochem and changing Cl to Cn, right? So that's all I'm going to do. I'm not going to draw it because I don't have enough room. So I'm just going to write it right where this is, okay? So it should be a dashed Cn. And that should be your product for the first reaction, okay? For the second reaction, you're going to do PbR3. PbR3, which is what's written here, is going to take your dashed OH and turn it to a wedged Br, right? And then NaCN and DMF is going to do SN2. So it's going to take your wedged Br and turn it to a dashed Cn, right? And right away, you can kind of already see that 1 and 2 work. So like, why do the rest in a way? But just in case if this answer choice had more than 2 options, right? I think this question only had 2 options as an answer. So like you would have been safe. Yeah. But we'll do 3 and 4 just to run through the mechanisms, okay? So number 4 is a lot simpler. Let's run through that one first. So if you have OH with TFCl, TFCl is not changing stereochem, right? This is just converting OH into a good leaving group. So you get that with a dashed OTF. And then when you do your SN2, you're just going to take your NaCN, which is really Cn minus, bang, bang, and you get the same structure but with a wedged Cn, right? And right away that doesn't match up because 1 and 2 are dashed. So let's see what 3 is going to give us. Okay, so 3 is a bit of a jerk of a question. So for number 3, you have OH, right? And OH is a pretty poor leaving group because if you kick it out, it becomes OH minus, which is a super strong base, right? And we don't want strong bases because then that's going to deprotonate things and change our whole reaction. So what we have to do is we have to convert it to a good leaving group. And the way we're going to do that is by taking the oxygen, grabbing an H, and kicking out Br, right? And when you do that, you make water. Oh boy. Give me 1 second, guys. Let me write this a little bigger. I'm trying to erase the top half here. So you make water, right? And water is a good leaving group. So we're just going to kick it out. When you do that, you get a carbocation, right? And remember what we said earlier about carbocations. Do carbocations have stereochem? And the answer is no, they don't. So if I add Br minus onto here, it's going to add one of two ways. It's going to add either wedged or it's going to add dashed, right? And if I have a wedged BR and a dashed BR, now I have two products. I have to do an SN2. Now the SN2 is going to give me two products. So in this case, reaction 3 also does not work because it will not give me only one major product. It's going to give me two products. So because of that, 3 is crap and 1 and 2 are the answers here. Okay? Okay. Let me give you guys another one. Okay, let's do another question, guys. I don't know why my laptop's blowing up. Okay, I don't have friends. So let's do elimination. Okay, so we're going to do this question next, okay? So copy that down. So I can get this to stand up. Cool. So copy that question down, and then we're going to run through it, okay? And like I said earlier, the recording is going to be saved. So if you guys want to look at this later, feel free and whatnot. It's a little bigger. Okay, so your first step now is to identify which reaction we're dealing with here. Bum, bum, bum. So for this guy, this reaction is going to be E2. And we know that this reaction is E2 because we have a secondary leaving group and we have a super strong base. Now, this base that we have here, it's called tert butoxide. Tert butoxide is a bulky base. This is the only bulky base that you guys are going to encounter, okay? So there are two bases you're going to use in this course, bulky and slim. Bulky bases I equate to my fat uncle at Thanksgiving because all he does is eat and eat and eat, right? And then I have my skinny aunt who brings her Weight Watchers meals and only eats those and like doesn't eat dessert like a weirdo because like we're Italian, you know what I mean? So this is going to do E2 because we have a bulky base. Now this bulky base, the first thing you want to do here is you want to look at your bromine, right? And you want to look at the adjacent hydrogens. I have a wedged hydrogen here. And then I have a wedged H here and a dashed H here, right? Now, this is my fat uncle, right? You guys probably have one of these. They got the beer belly out to here. They're chilling. They're living their loving life, right? So think about this guy. It has one hydrogen available, right? Does my fat uncle fit into his skinny jeans from senior year of high school? No, right? So it's not going to grab this H. Instead, it's going to come and grab one of these H's. Okay, so it wants to come to this carbon here, right? It wants to grab one of these H's. Now, the question is, does it matter which H it grabs? And the answer is yeah, it freaking matters because we can only take a hydrogen that is opposite stereochemistry of my leaving group, right? And that's a rule. So my leaving group is wedged, which means that my base can only grab a dashed hydrogen, right? So it's going to grab the H, push those electrons there, and then kick out the bromine, okay? And because of that, try to draw that product based on those arrows. So try to draw the product based on these arrows. Okay, so we didn't touch the top methyl group, so that's going to stay the same. Bromine left, and we're just left with that double bond. Okay? And this is a double bond. Right? So that's our product. So now let's run a similar question to this one, okay? So this is our fat uncle. This is the only fat uncle you guys are encountering. Okay? Let's give you another one. Now, this reaction is also going to be E2 because I have a secondary leaving group and a strong base. Right? So I want you guys to take a minute, copy it down, try to draw the product, and then we'll run through it together. Someone asked, what's the structure of OTF? If you look on that handout I gave you guys, the posted document, I have them all on there for you. On this slide, it'll tell you OTF is at the bottom here. Okay, so if you just look at the bottom here, that guy, that's the structure of OTF there. Okay. So you don't necessarily have to ignore a solvent in an E2 reaction. What you want to think about actually is that anytime you see a strong base in a solvent of itself, 9 out of 10 times it's going to be E2. Because if you put a strong base in, say, water or something, it's going to spend so much time interacting with that solvent that it won't actually perform the reaction. So usually we just toss it in a solvent of itself. But as far as the mechanism is concerned, don't worry about the solvent. It's, essentially useless for E2. Okay, so now you want to look at this base, right? And the first thing I like to do, like I said, I like to go to my leaving group, and I'll draw in the hydrogens that are next door. Right? And then you want to ask yourself, what kind of base are we dealing with here? Well, here I have OET minus, right? What does OET minus look like? It looks like this. Look at that frail little oxygen with its carbon structure, right? That shit, my friends, that is my skinny ant right there. Case in point, popped out 3 kids, still looks like she's 29. That's the skinny ant, okay? She's fitting into skinny jeans. She's partying on the weekends. Shit is happening, okay? So that's your skinny ant. Now, skinny ant obviously is fitting into those skinny jeans because she's going out every Friday night like she doesn't have kids. Sorry, family stuff. But so we're going to want to go where we don't have as many hydrogens because we don't want to eat that much food. This carbon has 1 H, this carbon has 2 H's. So this guy's going to prefer to go here. Before I can actually grab that hydrogen, though, I must ask myself, is this hydrogen opposite stereochemistry of my leaving group? And the answer is yes, it is. So after that quick check, I can come in grab it, drop it down, kick it out. Okay? And that's essentially going to be the mechanism. Okay? So then you get a double bond here. Now I'm going to drop two answers and you guys are going to tell me which one's correct. Okay, I have two answers drawn here, A and B. Would both answers receive full credit on an exam? Yeah, A is correct, right? Good work, guys. You never want to put stereochemistry on a double bond, right? You guys just learned that double bonds aren't chiral centers, so you don't want to put stereochem there. You want to leave everything planar. Okay? All right. Everybody good here? Okay, if this was a bulky base, if you were a bulky base, you were coming over here. Right. Bulky base would have grabbed here. This guy was able to grab here because it's a small base, so it can fit in where there are less hydrogens available. And this hydrogen is also opposite stereochemistry of my leaving group, right? So because they're different stereochem, and because it's a small base, this hydrogen is able to be taken. Okay? And then a lot of you guys are asking about the reverse situation, right? What if this hydrogen was wedged, right? And my leaving group was wedged? Let's do an example together to figure that out, okay? Yeah, a lot of you guys are asking that, so let's do it. And we'll use okay, guys, let's do this one next. So you have minus OMe over MEOH. Okay, guys, let's run through it. Okay, so OMe minus is a small base, right? It's minus OCH3. So that's tiny. So the first thing you want to do is draw out those adjacent H's, right? I have a hydrogen here and I have two H's here. Oh, did I do it again? Fuck. Sorry. Okay, can I make a quick last minute change, guys? Damn it. Quick last minute change. Make that CH3 group wedged. Okay, so I changed this real quick just to make my point because I wasn't thinking apparently. So we drew out our adjacent hydrogens, right? So I changed the problem real quick. And now we notice this is a small base, so it wants to go here, right? And it's looking pretty good. But what we notice now is that my hydrogen and my bromine are the same stereochem. Because of that, I cannot go here, right? Skinny Ant wants only one serving, but someone pressured her to go for dessert, okay? So we cannot go here because they are the same stereochem, right? So small base wants that H, but because it's the same stereochem as my leaving group, I am totally incapable of grabbing it. So I have no choice but to come down here and grab it, okay? All right. So you should get that as your answer. Okay, anytime, guys. Happy to help. All right. Okay. Now let's say we had a bulky base here. It would have went here anyways, right? It wouldn't have even tried there. So a bulky base would also give the same exact answer here. They would have both given the same answer. This marker sucks. Okay? All right. Now let's give you guys something a little more challenging, right? So let's give you the 3% of the time that chart doesn't work. Now, the 3% really isn't all that terrible. Okay? It's not necessarily that you can memorize when not to use the chart, but it kind of makes itself known. Okay? So I think we're good on this. Yeah, okay. So let's move on. So I'm going to give you guys a question from a past exam that was a past mechanism question, just to give you guys an idea of where they've tested it out before, and how to know when it's coming your way. This says CH3, CH2OH. Not sure if you guys can read that. Okay, so you guys copy this, and then I want to read you the exact wording. So this is CH3, CH2OH under the arrow. Richard. So do the exceptions. Yeah, essentially, Richard, you're on the nose, 100%. That shit's just going to involve some resonance and crap. Okay. So this guy, I just want to read the question to you guys, like I said. I don't know why I just put it away. I'm losing my mind. Okay. The following Savolysis substitution reaction gives two products, 1 and 2. Using the curved arrow formalism, show all bond making and bond breaking steps leading to product 2. For clarity, draw out all intermediates. So the key word that they tell you here that you should instantaneously recognize is savolysis. What does savolysis mean? Savolysis means SN1. Okay? So usually they'll tell you it's some kind of savolysis if they're giving you two products. Because normally you would look at this guy and you would say, well, this BR is primary, right? So your brain would go SN2. But because they tell us savolysis, it must be SN1. What else changes the game in this question is the presence of this double bond, okay? Because of that double bond, when we create a carbocation, right, instead of just having a plain old primary carbocation, we're going to have a primary allylic carbocation, which has resonance. And because of that resonance, it makes this carbocation about the same stability as a secondary, okay? So really only look for those deviations if you have the possibility of resonance. If you don't have the possibility of resonance, your chart's usually pretty on point from what I've seen in my experience with the course, okay? So now they want the mechanism for product 2, right? So let's run through how we would do this. And yeah, savolysis is always going to be SN1, Peter. So BR, let me move this closer. I don't know why I should move it back. I just like when it's close for you guys. Okay, so BR is just going to fucking leave. And it's like, bye, bitch, I'm out, right? Kind of like Thanksgiving break. You guys are just going to leave and be like, bye, Stony Brook. Pick you up when I get back, maybe. So that shit leaves. And you get that carbocation, right? So then all you can do is add this shit, right? Add it on, and that gets you product 1. But we don't want product 1 here. We want product 2. So we got to be a little fancy schmancy. We got to move this double bond over because that shit's 2 points. So draw out your intermediates, guys. You move that shit over. Now you have a tertiary allylic carbocation. The Orgo gods are praising you because you've created the most stable thing ever. There's stuff more stable, but for right now, we'll call it the most stable thing, right? And now this oxygen is just going to come in and be like, hey, thanks for opening up a spot. Yeah? Okay. Now, when you add this oxygen, you can't just draw an arrow and then draw an arrow to the product, right? You have to physically draw out what it's going to look like. And you're going to see you have an oxygen attached to CH2, CH3, that's the octopus looking thing, hydrogen plus charge. You want to, for full credit, you always want to show that deprotonation step. Okay? You guys want to do as best as you can on exam 3 because that will give you an edge up when approaching your final. Okay? Okay. Hopefully this makes sense to you guys. So if you see a fucking double bond and a primary leaving group, think SN2, but also think, oh, SN1 can work, right? Your solvent is also protic, right? So the solvents necessarily will not always tell you SN1 or SN2. However, they have impacts on the reaction. So the solvent stabilizes this carbocation in a sense. And because of that stabilization, that's another reason why we want to go the SN1 route instead of the SN2, because we have something to stabilize that carbocation. Okay. Everybody good there? I think we're good. Let me give you guys another one. Let's do some E1 shit. And I know you guys messaged me questions, so I'm going to try to get to as much as I can through them. E1. I know what we'll do. Okay. So E1 is fun It has a little bit of your exam 1 material on it. So I personally find exam 3 useful because, yeah, it's a shit ton of crap that you're learning, but a lot of it is cumulative in itself. So it kind of prepares you really well for the final. So let's do this question here. Now you have acid overheat. When you have acid overheat, 9 out of 10 times, that's E1. Okay, so acid overheat will give you E1. Hopefully you guys are recognizing that SN2 and E2 are very similar reactions, right? They both only have about 1 step to them. They don't have an intermediate. But when it comes to SN1 and E1, those are pretty similar because they have carbocation intermediates, right? So hopefully you guys are getting the gist of that. Someone asked, will they tell you it's Savolysis or will they have to figure it out ourselves? In a mechanism, they're usually nice and they'll give you that hint. I'm gonna run for another hour or so, most likely, just because I want to get to epoxides and everything and synthesis for you guys and protecting groups. So probably another hour or so. And don't be scared, okay? You're gonna be phenomenal. Who's scared? Indominus. You're like the Indominus Rex from Jurassic, because that's pretty sick. I went to Universal over spring break last year. That was chill. If you're scared, just come see me on Fridays. Bailey's also scared. All right, Bailey, we'll take care of you. Don't worry. Just, guys, come to my office hours. Go to any TA's office hours. All the TAs are freaking incredible. They're all super nice, and they'll love you and take care of you. So just abuse the shit out of them. Okay, so let's say you approach a question like this on your exam, right? And let's say your exam is pretty much, let's just say you get there and you have no fucking clue what you're doing and you're fucked and you're like, oh my God. And you just start having a panic attack. Now, I've done that before. I think it was my Orgo 2 final. I got to the exam and I had like a straight up panic attack because I looked at it and I saw the first question and I was like, oh my God. Like, I don't know how the fuck to do this. What the fuck? Like, I'm just screwed. What am I going to do, right? So if you get to that point, this is what I want you to do. Dumb it down for yourself, right? Put yourself in like a TA's shoes almost and just try to dumb it down and sit there and look at this, right? And say, okay, like oxygen has lone pairs and I have a positively charged hydrogen. So I may not know much, but my ass knows that oxygen is grabbing a hydrogen because hydrogen's a hoe, right? And that's what hydrogen's gonna do. Okay? So oxygen's gonna grab hydrogen because it's a hoe, and then we're just gonna make the compound that results here. And you get water now with a plus charge. And hopefully at this point you start thinking to yourself, oh, wait. I know this, right? Water's a good leaving group. I learned this. Somebody fucking taught this to me, so I know it. So then you're just going to kick out the water you made, right? Use the stuff you guys have known and learned. You guys are smart. You guys have so many tools, right? Figure it out. You've learned most of this already in past exams. Now it's just kind of putting it all together. Okay, so now you have a carbocation. Anytime you form that carbocation, what's the number one thing your ass is going to ask yourself? Can I shift to a greater stability, right? Carbocations can never be pleased. They're never happy. It's like what you guys are going to experience when you go to Thanksgiving dinner with your family, right? And they ask you what your major is for the 20th time. You're just not going to be happy with what you tell them. So this carbocation is not happy, okay? It's just sad. So it's going to shift. And we're going to do a hydride shift. Sorry, not a lefty. I'm trying. So when we shift, we now get a tertiary carbocation. Okay? So you're almost done. You guys are like 97% of the way there. That's all you can do with that H plus step. Okay? From here now, because it's E1, we know we're going to form a double bond. In E1 elimination, you are always forming the most stable double bond. Okay? So if I want to form the most stable double bond, heat is going to allow me to rip off a proton or rip off a hydrogen. These hydrogens are the same, right? So let's say I take off this hydrogen, or I can take off this hydrogen. It's whatever is adjacent to that plus charge, right? If I take off this H, I get that double bond. If I take off the top H, I'm going to get a double bond that looks like that. I don't want that double bond, right? Because this is a primary. This is tertiary. But here I have a secondary and a tertiary. So this double bond is going to be more stable. So that double bond is then going to be my major product. So that's why I grabbed this hydrogen here and not this H, because this will get me the more stable double bond. So my arrow is just starting at the bond between the H and the carbon, and it's ending here at this bond. Okay? And that's essentially E1. Let me give you guys another example to try out on your own, okay? Just lay that back for a second. Yeah, who said that? Yeah. Hydrogen's always a hoe. It's just, sorry if I'm offending anybody. But yeah, it's a hoe. Okay. So now let me give you guys another example. Somebody asked if the OH should have stereochem. It doesn't have to, because you're just going to kick it off and make it a carbocation anyways. So it's irrelevant to have it with stereochem. So you may not see it, but it is a chiral center. So that's a good thought. Okay, guys, copy this down and try this one for me now. Those are just methyl groups on top. No, you don't have to show it takes the H. Indominus, I don't know what your name is, but it's funny you say that. I actually just changed my major. So now I am thinking about going for teaching. I don't know about orgo, but I'm definitely considering teaching chemistry in the future. Okay, guys, copy this down. Try this one out. First, you want to identify the reaction, and we know it's E1. So then from here, try to figure out what the product is. I'll give you guys about a minute and a half, okay? And then we'll run through it. Okay, guys, hopefully you have an answer. Let's run through it. So, like we said earlier, we know that this guy is going to come in and grab the H. So you get your water. Let me see if I can change out the marker. Then you kick out the water. Oh, that's better. Okay. Kick out water. You get your carbocation. Right? And then we know carbocations can shift to a higher stability. So we're going to hydride shift again, right? Bond to carbon. And now it's more stable. Now I have to form the more stable double bond, right? Let me see if the color turns up. So I can either grab this H in red to form the double bond, or I can grab this H in blue to form the double bond. Which hydrogen is going to give me a more stable double bond, red or blue? What do you guys think? Yeah, the red hydrogen, right? The red H is going to give me a much more stable double bond. So I'm just going to pop that guy down. Right? And then that's my final product, and that's it. And yeah, I'm going to be a TA for Orgo too. So we know to form this double bond because we have heat present. Right? That's how we know we're going to pluck off this H. Okay, guys. So far, so good, I hope. All right, guys. So let's move on to epoxides, okay? I'm going to take a step away from elimination and substitution because elimination and substitution is such a large topic that I could literally spend like 4 hours on it alone. But let's move on to epoxides, and we'll run through the different mechanisms, and then hopefully you guys will see that they're very simple, very to the point. Do you guys remember BR2 mechanism at all? If you do remember BR2 mechanism, epoxides are very similar to that. They just have specific conditions, okay? Okay, so epoxides. The thing we want to know with epoxides is that you have two conditions, acids and bases, right? So the first thing we want to talk about is how we form an epoxide. So to make an epoxide, you usually start with a double bond, and then you're given a reagent, MCPBA, or you might see on some old tests RCO3H or RCO3H. Either or will do the job for you. So making an epoxide is just the oxygen triangle thing, right? Where you could have both wedged or both dashed. Right? So MCPBA or RCO3H will give you either an enantiomer. They'll give you both, and then you just go from there. So epoxides will usually give you two products. You can have base catalyzed epoxides. If you're in base, you'll attack the least substituted carbon. And I'll show you guys what that looks like. I'll give you a sec to copy if you're copying. Yeah, Katie, exactly. We're going to use BLAT. Right? Base is the least substituted. You guys may have heard that acronym for TAs. BLAT. Where base is the least substituted and acid is tertiary. Okay, so let's do an example then. So let's say we're given an epoxide. This guy, and it has an enantiomer. Right? And then on our arrow, we have OH minus and water. Okay, So the OH minus is going to attack the least substituted carbon of my epoxide. When I look at my epoxide, I have two things here. I have a tertiary carbon and a secondary carbon, right? So we have tertiary carbon, secondary carbon. Secondary is least substituted, so O minus is going to come in and attack and kick that guy out. When we come into attack, think of this identical to BR2, right? You have two wedges coming at you. You can't enter through the front, right? You have this giant thing coming at you, so you can't go through the front. So you're going to have to come around back, okay? So the OH minus is then going to come in on a dash. When it comes in on that dash, this guy gets flipped over, or flipped up rather, and stays O minus. ENT is just an enantiomer, Syed. So ENT just means that you could get this guy, or you could have been given this guy. Your epoxide could be either version. So it's just the enantiomer. Then you have an O minus, right? So you're going to have to protonate it with something. So you protonate with water. And then you get this guy plus its enantiomer. Right? So when we're talking about epoxides, what you guys hopefully realize, or what you notice, is that it's identical to what you've already learned, just a different aspect, right? And that's kind of what this exam is getting at. Okay, so this is a base example. Let's do an acidic example together, okay? I'm just going to erase the top. I'm not going to erase this. So if you have acid or acidic conditions, you are going to attack the tertiary position. Okay, if you have acid, you're attacking tertiary. So with acid, if you have a tertiary position available, right, that's going to be your sole major product. If you have a primary and a secondary position available, you'll get a mixture of both, okay? But for right now, let's just focus on the tertiary, because that's how you guys should see it on your exam. So let's do the same example we just did, but we'll change it up a bit. So you have that guy, and then we'll change the conditions to be H plus over CH3OH. So epoxides are essentially the same mechanism. Acidic conditions has two more steps than basic conditions, one or two more steps than basic conditions for acid. So the first thing we want to know here, right, this is H plus over CH3OH, is that oxygen has lone pairs, and we're an acid. So when we're an acid, we don't want to introduce a negative charge. So we're going to protonate to keep everything positive. And then you get OH plus. Now, when you have OH plus, that's very similar to a Br plus situation. So now all you're going to do is have your CH3OH come in and attack that tertiary carbon and kick that group out. Now remember, this oxygen, this epoxide, is in the front, right? It's coming towards you. So this CH3OH can't come in through the front. It's got to come around the back. And when it does that, this guy gets pushed down to become OH on a wedge. right? And then the OCH3H has to come in on a dash. When it comes in from the back, you have a methyl group already in the back. So this guy comes in through the back and pushes your methyl group forward and out of its way. And then that has a positive charge. Then your last step, like always, is just to deprotonate. And you get that as your final answer plus the enantiomer. Right? Everything has a freaking enantiomer. Okay, so those are your two sets of conditions that you're working with here. Okay, I'm going to give you guys an example to try out. I'll leave the acid up there, but I'm going to erase the base. Oh, that doesn't make sense. So you have MCPBA here, and then you have H plus with water, okay? So take a minute, try that one out on your own. So when I write plus enantiomer, I'm only writing that because on an exam, they'll usually write it for you in the answer choices. So I just want you guys to be comfortable with seeing it. All right, guys, do we have an answer? So MCPBA, hold on, blah, blah, blah. Yeah, okay, so you guys are good. I'm glad you guys are learning stuff. That's helpful because I feel like in this format it can be difficult. So MCPBA is just going to make our epoxide, right? So let me get rid of the H plus in water just for a sec. So MCPBA just makes the epoxide. When you're making the epoxide on your own, you guys are able to choose whether you want to make it wedged or dashed. I like to make them wedged. Right? And then dashed methyl, don't forget that methyl group, plus an enantiomer because I could have made the other one. What I noticed on your papers the past week is that when you guys are making your epoxide, you tend not to give this methyl group stereochem. If you're introducing stereochem on one of the carbons, make sure to introduce it on the other carbon as well. Okay, guys? So make sure if one carbon has stereochem, then the other one also has stereochem. Then we have H plus in water. So I'll give you guys another like 30 seconds. Try to attempt this mechanism on your own. Okay, it's good practice for you guys. No, you guys are not responsible for the mechanism of this. I don't know it. The professors don't know it. Nobody gives a crap. Don't worry about it. That's a great question. Okay, so hopefully you guys have your first arrow protonating the oxygen to give you a structure that looks like this guy down here. Right? And then we know we're in acidic conditions. The reason I know I'm in acidic conditions is because I see an H plus. Anytime you see a minus charge, that's when you're in basic. So that's what you guys want to look for when you're indicating acid versus base. Okay? So because I'm in acidic conditions, I have a tertiary position available. So I'm going to have water come in, attack the tertiary, and kick out that OH. Okay? When I do that, you're going to have this guy come in on the dash. So you get wedge OH up top, right? Because this bond here is just being kicked up. So it stays on this carbon. Then you get your dashed water. And then you have your now wedged methyl group, right? Because we're coming in through the back, the methyl group's in the back, so we got to push it forward, okay? And then your last step, like always, is just to deprotonate. Please, please, please make sure you guys draw your intermediates on this upcoming exam, okay? Get all the points you possibly can. The more points you get now, the less you need on the final. Okay. Few things I want to mention. Thing number one, MCPBA, right? It gives you that syn addition of oxygens, but the actual epoxide mechanism, whether it be acidic or basic, will give you anti-addition of whatever you're adding. Okay? So just keep that in mind. You're referring to the first example. The first example doesn't have a bond rotation. So bypass this bottom guy for a second. When you look at this top example, right, carbons 1, 2, 3, and 4, they're all in a zigzag and they maintain the same configuration. The only thing that's happening in this top example is this bond is pointing up here and then I'm pointing it down. I'm not rotating anything there, so the stereochem is correct as it's written. Hopefully that clears it up for you a little bit. Okay, so this is epoxides in a nutshell. How are you guys feeling on epoxides after this? Are you guys pretty okay on it? Let me know, please, so I know if I need to spend more time on it or not. Maybe I'll give you guys one more example to do, and then we'll assess. Let's do one more example. Much better? Good, good. Okay. As long as you guys are feeling better on a topic, that's what matters. I just want you guys to be as successful as possible. Okay. Let me give you guys one more example to try and run. Actually, let's do two more examples. We'll do this example, and then I'll give you a spicy version. Okay, so do this guy, and then I'll give you a spiced up version. So this is MCPBA, and then it's OH minus over water. I still can't draw arrows to save my life. Okay, so MCPBA and then OH minus with water. The only other reagent that will work aside from MCPBA is RCO3H. I'm not sure if you guys learned it this year. I know it's been taught in previous years. Okay, while you guys work on this, just something I want to say real quick. A lot of you guys want more practice problems and stuff from TAs, like you guys kind of just run through the lot of them, and then you want some more. My best advice for that, honestly, is the examples we're doing right now and the examples that TAs give you in office hours if they give you any extra questions. What I highly recommend you guys do is take those problems you're given, right? Redraw them on a blank piece of paper and create your own problem set and do them over, right? Because right now you guys feel like you're getting this as you follow me along, which is great. But make sure that you can also do it on your own without my assistance, right? So if you copy them over to a separate sheet of paper and then attempt them, not only do you have the answers written down already, but now you have this video to follow along with, or it's just a better assessment of how much you actually are learning and retaining from all of this, right? So make sure you guys are keeping that in mind. If you want extra practice problems, just take these problems, write them on a separate sheet of paper, and then you have an answer key and you have an idea of how you're doing so well, doing so far in the class, okay? Okay, I'm done spieling. Let me give you guys another minute or so, and then we'll run through this. And then we'll do oxidation and reduction real quick, because those are easy. Okay, guys, hopefully your answer should look something like this. Or this. Those should be the two products you guys got. How many of you guys got that? Or you should have wedged methyl, dashed OH, wedged OH, dashed methyl, wedged OH, dashed OH. Good, good, okay, yeah. So you're gonna get, sorry if I jumped the gun. Yeah, okay, I'll do the mechanism anyways. So let's say MCPBA, right? Let's go with dashes this time, just to spice it up. Now I have my dashed epoxide in my wedged methyl group, and then I realize that I'm in basic conditions because I have an OH minus. OH minus is base, so we're going to attack the least substituted side of my epoxide, come in, kick that guy out. Then my next intermediate should be that with an O minus, and then the wedged OH. And then my last step is just to grab an H from water and protonate it. And it'll lead me to this guy. So minus grabs H, because it's a HO, and then you just pop that off. Okay, so let's do another one. The one I'm going to give you next is from a past exam. This one is a little spicy, okay? Just going to erase this part. I'll leave the rest for another second. So this one, they want you to choose the expected major product of the following reaction, okay? So it's going to have answer choices and a mechanism. Okay, guys, so run through this mechanism and then compare your answer to the answer choices. Okay, guys, take a minute, try this one out, and then we'll run through it. And I want you to pick what answer choice is correct here. Okay, take a minute, try this one out. And you can't see the last answer choice. Okay. Either. So this is a multiple choice from a past exam. Test it out. Once you guys have an answer, drop it in the comments. Okay, guys, what did we get? D, E. No, E. Okay, we didn't want D. Yeah. Okay, E. Yeah, you guys got it. E. Good work. let's talk about why it's E and why it's not D, right? Because those would have been the two contenders here. So the question here is, why are we going for E and why not D, right? So I think you guys saw it. Here, when you do your mechanism, you protonate, right? So you get that guy. Then it's acidic conditions, so you attack more substituted. Kick that out. Right? And you get something like that. And then you're just deprotonated. So your final answer that you get based on what they give you should look like this. Yeah. And the first thing you guys should hopefully realize here is that this carbon chain is different from your answer choices. Do you guys see here, if I were to number these 1, 2, 3, 4, 5, right? Let's just take a look at the answer choices. Let's just number C. 1, 2, 3, 4, 5. My carbon 4 and my answer is pointing up. Their carbon 4 is pointing down. So they rotated the bond. Right? So they rotated the bond on you. Because they rotated the bond, D becomes an incorrect option choice. Okay, yeah, it has the opposite stereochem factor, but because carbon 4 was pointing up on our answer, and in their answer it's pointing down, they rotated it. Let's do a quick run through on how to rotate bonds, just so that we're all on the same page. So the way I like to rotate bonds is I take my guy, right? I take this and I draw an x-axis through my compound. And I say, okay, anything that crosses this line must change stereochem. So I number my carbons. I'm going to take carbon 4 and flip it down. So that means carbons 1, 2, and 3 stay the same. So carbons 1, 2, and 3 all stay the same because I'm not moving them. Carbon 4, I want to rotate down. So I'm just going to draw it down. Carbon 5 then goes up. Now, carbon number 3 did not cross my dotted line, so its stereochemistry remains the same. Carbon 4 crossed my dotted line, so my stereochem changes. Okay, and that's how we get option E as our answer choice. CH3OH is acidic because we have H plus over CH3OH. That's what makes our reaction acidic. Okay, guys, so that's how we rotate the bond. Everybody cool with that? Let's do some oxidation reduction stuff. I'll do like 1 or 2 examples on that just to get through them. And then I want to do synthesis with you guys because that's guaranteed to be 10 points on your exam. And I want you guys to be able to get it. Well, I'll leave the rest of that there for you guys in case you need it. Okay, so we'll call this question 1. Question 2. Sorry if you guys can hear the squeakiness of the marker. I'm just trying to write dark enough. If you had NaOCH3 above the arrow, then it would be negatively charged. So OCH3 would be of basic conditions. Actually, who is that? Brianna, you actually raised a really good point. You guys copy these down. But I saw a lot of you guys having confusion with that, especially when it comes to substitution elimination. You guys kept getting confused on the difference between CH3OH and CH3O minus, right? So this is a strong base with the minus charge. With the proton, with the hydrogen there, it becomes a weak base. So this would prefer E2, depending on the conditions you're in, and this would prefer SN1. More specifically, this would prefer salicylisis, depending on the conditions you're in. Okay, I hope that clears that up. Okay, so LiAlH4 and Jones, and then I'll give you guys one more of these, and that should pretty much cover it. And I know you guys have lecture in the morning, so I don't want to keep you guys up too late. And the last one's NaBH4 over ETOH. Okay, so take a minute, do these. Hopefully you guys have this in front of you. This page will be really helpful for these. If you guys have this in front of you, please use it. It will be super duper helpful, and it will tell you exactly what to do. These oxidation reduction reagents can affect more than one thing. So in the case of LiAlH4, you have 2 double bonded O's. It's going to reduce both of them all the way down. So instead of 2 double bonded O's, your end result is 2 OHs. Okay, and that would just be the answer. Yeah, definitely put that crap on your index card without a doubt. Don't try to memorize that shit. That's too annoying. Okay, number 2 is Jones. You have a primary OH and a secondary OH. Jones affects both, and if you guys have your thing in front of you, what you'll see is if you look on the left-hand side, all the way at the bottom, you should see primary OH becomes carboxylic acid, and then secondary OH becomes double bonded O. The way you're going to take this guy here and turn it into carboxylic acid is just redraw exactly what you have. You see how I didn't move that OH? Keep that OH and then just add the double bonded O there. And then you add the double bonded O there. And that's it for that one. Okay? Then for the last one, NaBH4 is super duper weak. NaBH4 cannot reduce carboxylic acid. So this is going to stay the same. The only thing that's getting reduced here is this double bonded O. This is more of an index card thing. They're not super complex, but it's just a good idea to know how to use them in order to do well. Okay. I'll leave that up for another minute, and then we will get started on synthesis and protecting groups. Okay, guys? In response to Peter, yeah. Number one, if this shit had like 20 double bonded O's, it would all become OH. Yeah, Saeed, ETOH. If you look on the very top right of your paper, I wrote it as a correction. Where is it? Right here. Right? There's some typed up stuff there. In lecture, he showed it as NABH4 ETOH. It's just another acid. It's like water. It's just a solvent that you're going to use. That's how he showed it in lecture. So I just want to make sure you guys had what he showed. And in response to Richard, HNMR and CNMR should be the last topics on your third exam, as far as I know. And also, guys, on Friday night, you guys have the mega review, and HNMR and CNMR will be covered in the mega review, so make sure you guys watch that. Yeah, H2CrO4 is Jones. Jones will usually be H2CrO4 over H plus and water. Okay. Cool, guys. So make sure you tune into the mega review on Friday. That should be super helpful, and they're going to cover HNMR and CNMR, and the TAs are phenomenal. So definitely live echo it or watch it sometime this weekend. Okay, protecting groups. For protecting groups, you guys learned two reactions. The two reactions that you learned are how to put it on and how to take it off. But I don't like that terminology because it's misleading the way that you guys learn it. Oh, shit. Oops. We're good. I dropped the whiteboard.
Oh, okay.
It's all good. Sorry. Oops. Yeah, I'm fine. I'm fine. Chem bloopers, facts. Oops. Just move this back. Okay. This is like my baby.
You okay?
Yeah, I'm fine.
Okay.
Sorry. Thanks. Sent the whole house into a frenzy. Yeah, I'm fine. Thanks, guys. Oops. Mega review. I think it starts at 4:30, but I'm not sure. PCC written out is just PCC. Okie dokie, guys. And now I set the dogs off, and now they're going crazy. Oops. Okay, so for protecting groups, you guys learned two reactions. The first one is putting it on. You're going to have OH, TMSCl over ET3N. Gives you OTMS. And then OTMS, TBAF. That will take it off. Okay, so those are your protecting group reactions. OH, TMSCl over ET3N goes to OTMS, and then OTMF, TBAF goes to OH. Okay, so those are your two protecting group. In a lot of things you guys read and a lot of things you guys see, it's gonna say that this is what puts it on and this is what takes it off, and that is accurate and that's the truth. That's what happens. However, when you guys are doing synthesis, you're working backwards. So if you have to go backwards on this, if this is the if this is the last step forward, then it's the first step backwards, right? So let's do an example and I'll show you what I mean, okay? Leave this up here for like another 30 seconds. And for whoever's still watching, congrats, we made it to 2.5 hours. Hopefully you guys are learning all the chemistry right now. Okay. So how do we know when to use a protecting group versus when to not use one? And the answer is functional groups, right? Anytime you have two or more functional groups, that's an indication that you're going to have to use a protecting group. If you have just one functional group, that's easy to work with. But if you have two or more, that's when you're going to need a protecting group. Okay? So what you want to do here is you can only protect an OH. So we have to convert these to OH. In order to convert them to OH, we can use one of two reactions. We can use PCC, or we could use Jones. It doesn't matter which one you use. Both will lead you back to the same answer. Okay, now the reason we need a protecting group and why this becomes an issue is if we cut here where the OH is, we're going to end up with a lithium on this side. And OH with a lithium causes things to explode. Okay, I don't know about you, but I don't really want things exploding on my exam paper or on an exam. So that's why we have to use a protecting group. So we have to use TBAF. And what TBAF is going to do is protect an OH. Now we get to choose which OH we want to protect. Here it doesn't matter because they're pretty much the same OH. So I'm going to choose this one and it becomes OTMS. And that becomes OH. And now while my protecting group is on, I can start cutting and doing what I need to do. So I'm going to cut right here. Right? And then I have 2 H2O. Make sure you guys are putting that when you're cutting. And then I have bang, 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 bang. Li. OTMS. And then I have step 1. That dude. Right? So that's all we have there. And now when we look at it, move on to this side now. This guy or this piece is 4 carbons or less. So we've achieved our goal, right? We took it to 4 carbons or less, so we're good. So a lot of mistakes that students make is they'll just go back and they'll take off the protecting group right here. Now, if you take off the protecting group, you put yourself in that exploding situation, right? So you want to avoid that. So we can't take off the protecting group just yet. We have to convert Li into Br first. Br and OH will not interact with each other. Those are safe groups to have together. Once you have that worked back to Br and OTMS, now you can take it off. So to take it off, going backwards, you use TMS, Cl over purity. You guys are an ET3N. And then it just becomes your OH. Okay? So that's all that's happening here. Okay, synthesis is fairly straightforward for this exam. I don't think the protecting groups are too terrible. I just think it's always best to put it on first and take it off last. Right, so your first step backwards, once you get your OHs, is to put on the protecting group right away, and then don't take it off until you have a Br and 4 carbons or less. Okay, let me give you guys a quick one just to try out on your own. And then I got some other stuff I want to cover with you guys, like intramoleculars. Okay, so try out this one next when you guys are done copying down, okay? And I'm just going to erase this top portion here. Chemical shift should be given to you guys on the exam. Usually they give them on the cover page. Just wait for that to come out and then you'll know for sure. But usually they give it to you. Okay, guys, so let's run through this. So the first thing I'm going to do here is I'm going to protect the OH, right? So I'm going to use TBAF. I'm going to make this OTMS double bonded O. From that double bonded O, I'm just going to use PCC, right? And now this is identical to the synthesis that we did before. And if you don't want to use PCC, you can totally use Jones. That's fine. This is just to get you guys practice working with it. So we cut. Double bonded O. And then we have OTMS. Turn that back into BR. And then take off your protecting group. And then someone wants to know, is it wrong to do PCC first? In this case, it is. So what happens here is if I do PCC as my first step backwards, right? What I'm going to get with that is 2 OHs. So going backwards, that looks okay to have, but going forwards, it's going to turn both OHs into double bonded O, and it's going to give us a product that's different than the one given to us. So in this case, we can't use PCC first. As far as the synthesis toolbox, like I said, just wait until the cover page is posted. They should give it to you guys, but I'm not entirely sure what they're planning on doing. I chipped off a piece of the whiteboard. Shit. Oops. Okay. Is everybody cool with these syntheses and all that kind of stuff? I hope so. There's just one more thing I want to cover, and then I'm going to have to end it in 10 minutes, unfortunately. But there's just one more topic I want to cover real quick. Okay, let's say you guys are given something like this. 1 second, I have the exact question. So this is another past exam question. Okay, we're going to talk about this question here. This is a mechanism from a past exam. This here is a dashed Cl, and that's a dashed I. These are wedged SCH3s. I'm sorry if I didn't get to some of your guys' questions tonight. I got through most of them. I had about 30 questions come in from you guys, so I got through a decent amount. If I didn't cover your question, just find me tomorrow in Frey. And then I can explain it to you in person. That's cool with me. Like I said, before or after the workshops, I'll be around. So just come find me in Frey, or Thursday, extra office hours at 1, and then Friday, office hours at 11, okay? So let's just run through this last idea, guys. So here, what do you guys think this reaction is? Do you guys think this is SN1, SN2, E2, or E1? Right, that should be your first step in all these questions. So what kind of reaction are we dealing with here? Hopefully you guys would think SN2, right? Because I minus is a pretty good nucleophile. What's the issue with this being an SN2? The fact that the stereochem here and here, it remains the same, right? So how do we keep the stereochem the same? And I think Jonas, Jonas just said it, right? It's gonna do an intramolecular reaction first and then proceed with the SN2 reaction. So here, what you're gonna see is that the sulfur is gonna use one of its lone pairs to do an intramolecular attack with that Cl. And it's going to create something very similar to the epoxide you guys have been seeing. It's called a sulf oxide, right? And it's going to create that intermediate. So anytime you have a sulfur on your compound, it can do the same things that oxygen can do. And oxygen can also do this, right? So you always want to keep this in mind. It's going to do an intramolecular SN2 followed by a regular SN2. Right, so now those are both wedged with the sulfur with a plus charge. It's mad ugly. Right, so now those are wedged with sulfur with the plus charge. And then you're just going to have I minus come in. Here it doesn't matter which side, but because they give you a product, just go with that side. It'll come in and then kick out that sulfur, and that will lead you right to this product. So this is a very short mechanism, but it's entirely applicable to what you guys have done. Okay, so I just want to keep you guys with that in your thoughts, that S can also do these intramoleculars. And sulfur just gets kicked out. So we just kick it out, and then you have some Cl minus floating around somewhere in solution. Right, so this arrow up top here is showing sulfur attacking that carbon, and then this arrow is showing Cl leaving. Okay, guys, unfortunately, that's all the time I have for tonight. I hope you guys found this super helpful. Best of luck, and just come see me in the CLCR workshop, and be sure to ask the TAs questions, and definitely watch the Mega this weekend. Okay, guys? Have a great night.